Welcome to today's lecture. So, today we are going to speak very much on some of these practical issues and practical aspects, and in fact, I would be showing you a very detailed case study which we had run down on one particular model, one particular deep neural network on multiple kinds of hardware units over there to really come and compare where they stand against each other. Okay. So, what I am going to do is this is going to be a bit of revision from some things which you had learned way back in your undergrad possibly, and that's about the computer organization and architecture. So, if there are current students who are in the second year or third year, I am not quite sure if you are doing these if you are doing this particular one, this particular lecture series, then you might be studying those at this point of time as well. Now, computer organization and architecture is quite an important subject which I keep on telling people from the engineering aspect of whether your machine learning algorithms, your AI systems would actually be working out pretty fine or not. So, today what I am going to do is in the last lecture we had done a bit of theoretical analysis on what is the total space required when just storing your model. What is the total space required when you are trying to do a forward pass and a backward over the model. So, that also has a dependency on the data size over there, and then we also discuss about what is the total number of operations which will happen when you are trying to operate anything on the model. Now, today what we are going to do is on the aspect of that, given that I have found out all of these criteria over there, what is my total number of operations which is going to happen, what is the total space I require in bytes to store it down, then what will happen on my side of the machine, and then can I keep on changing this number system precision over there to change something, and what kind of hardware would allow me to have a variable precision number system and which of them will not allow me to have that one. So, these are stuff which we are going to really look into while working out today. So, today's organization is something of this one, that I will initially start with something called as the code residence. So, code residence, so these are not concepts from machine learning as such, but these are engineering aspects about getting these AI systems working down. So, code residence is like if you have a piece of code with you, then does it reside on your RAM, does it reside on the hard drive, and then does it reside on your CPU cache, and how do these operations have a very significant implication on how fast you are going to really work it out. The next part is to come down to a very practical way of finding out your batch size. Now, we have been doing all of our update equations, update rules and everything under an assumption of a batch size. So, we just assume that this batch size is what is working out good, but then while I was doing it, you had realized that there was different batch sizes I was using for different kind of compute mechanisms. So, whether I was using a GoogleNet or a VGGNet or a RESTNet or a DenseNet, my batch size was always changing out over there, and what I did specify is that we try to pick up a batch size such that it fits perfectly within the RAM. It does not overflow, as well as it does not under consume the GPU RAM on which I am working it out. Now, however, I had not actually given an explanation at that point of time how to go on choosing around with this one, and how does it impact, like whether your model is big or small, how much is your operational space complexity, and how is it going to impact your batch size over there, and whether you can take down a decent size batch or not. So, this is where we are going to discuss it out exactly on how it impacts my batch sizes. Now, then I have GPU operation, and what does come down on a GPU operation, which means that if I have something which I am working down traditionally on my CPU versus if I want to work it out on a GPU, then transferring things from a CPU side onto a GPU side, what is the total amount of change which is going on, and then what are the hardware units which are being invoked, and whether there is some sort of a bottleneck which might come down because of certain features which are not supported within my computer system or within my motherboard itself. Okay. Then I would come down to acceleration and how and what acceleration is it and how it works out, and then we come down to a very practical example for case study. Okay. So, now for the first part of it, which is to understand code residence on my computer. Okay. Now, typically what I have on my PC is a hard drive. So, when you are defining, you are writing down some piece of code and then keeping it down, or you download a model. So, what we were doing down initially is that you have your these header files which you had called it out. So, that was loading onto your RAM from the hard drive. Okay. Next, you defined your network over there, or you downloaded your network over there. Now, when you download your network as well as when you are downloading your data, you see that everything was getting stored on your hard drive over there, and there was some root slash path being defined if you are a Linux user, and if you are a Windows user, then you have some drive letter colon slash and then your path definition which comes down over there. So, this is the part of the code which and the data which actually resides on your hard drive over there. Now, what for us would be that I have my model and I have my data set which together reside on my hard drive. Okay. Now, when I need to work it out on my RAM, then what I would be doing is I will have my model which consists of my parameters over there. Then I will have my model which will consist of my activation and gradients. Now, when we were looking into operational space complexity, we figured out two things. So, operational space complexity is typically greater than the model space complexity, and the reason it is greater is because you have the model space which is the weights and everything taken down over there, as well as you have those activations and the gradient of these activations which are also stored down, and that is what I am putting down in this extra block over here which is just activations and gradients. Okay. Now, what you need to keep in mind is that you cannot load the whole data set onto your RAM, and typically we were doing it in batches, which was a chunk of the data which was getting loaded onto my RAM, and this activations and gradients are what correspond to this data which is loaded onto my RAM. Okay. And that is how it's going to perfectly work it out over there. Now, this is typically an arrangement of how things would reside on your hard drive versus how things would reside on your RAM, and the data which resides on your RAM is just a small part of the data set which resides on your hard drive over there. Okay. Now, let us look into a very typical case scenario over there with certain numbers. Okay. Now, I have my hard drive, I have my RAM both present with me, then say my model which is of size 100 MB. Okay. Now, when I am trying to load a model onto RAM, which is I define this command over there, net is equal to torch.load, and then my path is given down over there. So, what it essentially does is that there is a connection via a serial ATA. So, there is a SATA cable connection between your hard drive. So, it will be a thin color, a thin blue colored or a black colored cable you would see, which connects from your hard drive onto your motherboard. Okay. And then on the motherboard there is a separate driver unit for this one, which is going to interface this protocol of SATA onto your RAM bus over there, which connects it back onto the RAM, and then via DMA transfer you can do all of this. Now, this part over there, if you look into your hard drive over there, so your hard drive's data transfer capacity is much lesser than your RAM's data transfer capacity, significantly lesser. I mean, your RAM can transfer something in the range of gigabits per second, whereas your hard drive will be something in the order of megabits per second. So, this part is a slower part, and you would see that it takes some time to load. So, if you are copying down some model from one part to the another part of the RAM, it would be significantly faster. So, you can have like just do a deep copy over there. So, deep copies are much faster over there because they are just copying down onto your RAM, whereas when you are doing a model copy, then it is much slower because your hard drive is slower. So, this is what will happen, and this limitation is something which you need to keep in mind as well. Okay. Now, the next part is that you have your data set. So, typically your data set would be about 100 GB over there, some hundreds of GB, very practical data set. So, we are not looking at say CFAT 10 kind of data sets, which are rather smaller, hundreds of MBs over there. But then if you look into the complete ImageNet data set, or if you are in the subsequent ones when we will get into temporal deep learning, so we will be understanding more about what happens down with say video data sets, and then they are really massive. Okay. Now, if I have a data set which is about 100 GB over here, then I cannot load everything onto my RAM, because typically my CPU RAMs are, so most of your machines will be about 8 GB of RAM or 16 GB of RAM, maybe 32, 64 GB of RAM. I mean, there will be very few machines which will have about 100 GB of RAM. I mean, that there is one back in our lab which has 128 GB of RAM, but that's one of the major massive machines where for a particular purpose we had to load the complete data set over there. But then most of our data sets are not 100 GB, they are something which are in the order of multiples of 100 GB or close to actually a terabyte of. So, in fact, we cannot also load down most of those data in one single shot over there. So, the idea over here is that you would be chunking a part of this data set over there and put down onto your RAM, and say that we are putting down some 100 MB of data at a point into my RAM. Now, when you were writing your piece of codes over there, you had the data loader function, and then you had something called as a batch size on the data loader, and you had a number of workers being defined, number of parallel channels per data loader. So, what it was essentially doing is that every data loader just loads down a chunk of this data, reads a particular part of the file on the hard drive and then saves it out onto your RAM. And this connection is also via SATA, because that is the only way your hard drive connects down to your RAM. And this is a slow process. So, what we do by putting down parallel workers over there is that we instantiate a number of parallel threads of this process, such that while one data is getting used via this model and there is some processing going on, there are other channels which are coming over there, and SATA as such is not just one single path. So, it is not like you can access only one region over there, but you can access multiple points on the hard drive coming down together, and then there is a limit on this one. So, how many channels your hard drive supports and how many channels your interface of the SATA controller over here supports, it is a trade off between that. So, if your hard drive may support say 8 SATA channels over there, but your interface controller on the motherboard might support just 4, then you can instantiate maximum 4. If you just write down 8 as the number of parallel workers on software, you are defining it, but then your hardware does not support that feature in any way. On the other side of it, your motherboard may have 8 SATA channels, but your hard drive might have just 4. You are still limited by 4 because defining more than that is not going to help you out in any way. Okay. Now, what comes down subsequently after that is that once I have this loaded down, next what I am going to do is I do a forward operation over there. Now, typically in my forward operation, what comes down is that the data passes from this part of the RAM and goes done as a feed forward through this model. Now, for each sample point over there, it is going to calculate an activation and also associate a gradient vector, a container for the gradient. You do not get the gradient calculated until you do a backward operation. So, that is not of a major concern as of now, but the space allocation is definitely over there. Okay. Now, you do a forward, you pass it through the model for each single sample from your batch over here which forwards through it, you will get down the activation and the gradients calculated and say that this is in the order of some 500 MB. So, if I have 100 MB of input data going down, it generates about 500 MB of this space coming down over here. Now, you can typically look down at this point of time on my RAM, I am consuming about 700 MB of space, and this is just for a data of 100 MB and a model which is of 100 MB size. Now, if I change this 100 MB and go down to about say 1000 MB, now based on that, this space over here we change over from 500 MB to 5000 MB. So, that would mean that this is about 5 GB, this is 1 GB. So, that makes it 6 GB plus another 100 MB over here. So, that makes it 6.1 GB of space which I consume on the RAM. Now, my model, my stationary model over there which just has parameters, that space is what is a constant fact, that does not get multiplied or anything over there, and this is what you need to keep in mind. So, your model might be smaller in size and still you will not be able to give down a very large batch size, because this activation plus gradients is what is something which is going to consume significant part of your RAM over there, and that is a trade off which you will have to calculate it out. So, since we had already done pen paper calculations of how to do it for one layer at a time, now if you repeat it down for all the layers, you will actually be able to get down your total space being consumed for your activation and gradients over there. Okay. Now, say that how do we calculate out the batch size? Now, this is critical, because this is where we were struck down in the earlier one as to how do we actually estimate out batch size, and is there some empirical rule of doing it. So, now what I said is that there is no straightforward empirical rule, it is something which is dependent on that you will have to actually find out what is the total space being taken down while the operation is going on, and it pretty much depends on that. And now, what we are going to look down is typically onto your CPU operation, which means that you do not have a GPU on your system, your model is not typecasted onto CUDA. So, there is no acceleration, there is pure CPU operations which are going on. Maybe there is an acceleration onto your CPU which we will see in later on point over there, where we had some multi-core CPUs available with us, and we used a very special precompiled library for Python which supported multi-threading onto it, and multiple pipelines being created for acceleration as well. So, that is what we will be doing on, but as of now let us consider just a plain simple thread, one single thread CPU operation going on. So, now I have my RAM available to me. Okay. Now, what I would do on my RAM is that I have some 100 MB of parameters which is available. So, this was the earlier case which we had looked on. So, my model space or parameters is about 100 MB. Okay. Now, what I do is I load a batch of data from my hard drive over there, and say that I have this each sample is about 100 MB, and then I load a complete batch over there. Okay. So, there will be some batch size into 100 MB is the total data size which comes down over here. Okay. Now, for each data point, what would happen is that I would get down one model activation. So, for each single sample I get down an activation and gradient, and similarly it keeps on going, and then at the end of the batch I have this one. So, this is for my forward, and then my backward, and then I have this one. So, now what that makes me come down is that my operational space as I would need is the total space consumed by my parameters plus batch size times my data size plus my activations and gradient size over there. So, for me it is something like this, that my batch size, my data size is 100 MB, my activation and gradients is 500 MB. So, this makes it 600 MB, and now say that I have a batch size of 10. So, it is 600 MB into 10, which makes it 6 GB over here, and I have 100 MB of model space over here. So, my total operational space requirement is 6.1 GB as of now. Now, typically if your CPU system has about 8 GB of RAM over there, you would see that your system operations and your operating system itself is going to consume roughly about say 1 to 1.5 GB of space over there. So, you are left down with merely 6.5, something like 6.5 to 7 GB of space, and now if we run this one with a batch size of 10, then I am already consuming 6.1 GB, and possibly that is the maximum I could consume, and typically I do not suggest that go down more than that. So, at any point of time any single program which you are running, as a cardinal rule we do not load it more than 80% of the space on the RAM. If that is the case, then what happens is that it needs to initiate a paging operation over there. So, it will start writing down to the page files, and that will even make it slower and slower for you, because you need to leave down some space for the system operations to keep on going down over there. So, in this kind of a scenario, a batch size of 10 for a system, for a CPU system which has 8 GB of RAM is something which is ideal, and this is a practical way in which you can calculate it out. Now, on the next side is let us look into the batch size for a GPU operation over there. Now, say that I have my hard drive on which I have my model which is of 100 MB, and then I have my data set which is of 100 GB over there. Okay. Now, typically what I would do is that first I would copy down this model onto my CPU RAM. Now, there are two aspects which you need to keep in mind. So, your GPU is a separate card which sits on top of your PCI slot. So, it is a separate PCI card which sits on the PCI slot, and it is connected just by these PCI buses, and PCI directly does not interface onto your RAM, and the CPU and say the processing units within a GPU, they do not directly access the RAM present on your CPU. So, your CPU might have 64 GB of RAM, that does not mean that your GPU is able to do it. So, your GPU might have its own 2 GB of RAM, or say 8 GB of RAM, or 11 gigs of RAM, typical numbers. Now, you have GPUs with about 16 GB of RAM to even massive ones like 24 GB of RAM. It depends on what is the use and what is the make you are doing. The more you go on that RAM side over there, the memory management and the cost associated with those high density and heavy speed RAMs is what increases the system cost as well. Now, typically when you have your operation going down over there, so the first part is where you copy down your model, which is you do a torch.load for the model, and that means that you have copied it down to your CPU. It still does not reside on the GPU. This is what you need to keep in mind. Okay. Next, what you would do is that you cannot copy down the whole data set because it is about 100 GB over there. So, what you can do is you can copy one batch of the data. So, maybe 1 GB is a batch of the data which you have copied down onto your CPU RAM. Now, if your CPU has larger size memory over there. Now, I have my the advantages over here is that in the earlier case when we were doing it on the CPU system over there, you had this additional space of gradients which was stored down onto your CPU RAM itself, but then here my compute is not running on the CPU, my compute is running on the GPU. So, my activations and gradients are something which gets stored on the GPU and not on the CPU. Now, on the other side of it, I have my GPU RAM available to me. Now, when I do this GPU RAM call over here, what comes down is this model is actually stored onto my GPU, and under typical conditions, if I am using the same number system precision. So, if my model was stored as a floating point number system on my hard drive and it is imported as a floating point number system, a 64-bit floating point number system on my CPU RAM, it will retain the same amount of space it would take. And then when I convert it as a .CUDA, so I do a net .CUDA, which is my typecasting. Now, this typecasting operator is which copies all of these onto my GPU memory over there. So, it will also be taking the same amount of space, and this copy is via a DMA transfer, which is much faster than a SATA transfer. And for that reason, you would see that while it takes longer to load a model from hard drive, it would take much lesser time in order to just do a typecasting conversion. Now, from your earlier experiences of data structure which you had done in engineering, you might consider that typecasting over there is just changing the resolution of an array. But over here, this typecasting operator is which moves something physically from one part of the RAM to another system device which has a different RAM of its own. Okay. And the model needs to reside on the GPU RAM. If it resides on the CPU RAM, it does not work, because the GPU processors do not have direct interfaces and memory connections onto your CPU RAM. It just can work if the data is present or the operators are present only on the GPU RAM over there. Okay. Now, from there, next what I do is I have my data loader. Now, within my data loader, what I was doing is, if GPU is available, then I always used to do a typecasting of the data, which means that there was a say data dot CUDA or input dot CUDA colon input dot CUDA open and close brackets. Now, what that did essentially was that this data which I had on my hard drive over from my hard drive, which I had chunked via the data loader and kept on the CPU RAM, I am converting all of that onto my GPU RAM space. So, I am just typecasting it, and that initiates a DMA transfer via which it does, and because it is a DMA transfer and on the motherboard itself, so that is much faster than a SATA load over there, and is what takes down. So, this is how it is divided onto my batch over there. So, I have 1 GB of data, which basically is a batch size of 10, and there are 100 MB of per sample space which it requires over there. Now, when I do the forward operation over there, what it does is that for each data point over there, it does a forward, and then it creates a activation and gradients over there. Now, these activation and gradients are what store on my GPU RAM. They are not present on my CPU RAM in any way, and that is where it really saves. So, now if you can actually try doing this one, take the same model, run it only on the purely on the CPU, do not typecast anywhere on the GPU. So, wherever you have a or what you can do is you can just set down on top of it, like where it does a check for the GPU if GPU thing. So, over there you can just put down that if GPU is equal to false, if GPU availability is equal to false. So, that means that even if the system has GPU, it will not pass through the GPU route over there. Now, then do a forward propagation on that and see. So, you would see that everything is what is changing on your CPU RAM. You can open up your GPU monitor and CPU RAM monitors and check out on this one. On the other side of it, if you are passing it via the GPU, you would see that the model starts exploding and the space consumption increases onto your GPU side of it. Now, this is the difference which comes down when you are operating on a CPU versus you are operating on a GPU, and then how to work it out. So, now here for this particular model, if I have a batch size of 10, then what comes down is that my per sample of data, I have about 600 MB consumed, and so over a batch size of 10, that would be 6 GB, and I have a 100 MB. So, this is a 6.1 GB. Now, if I have a GPU which just has barely 2 GB of memory, this will not be working down over there, because you need more RAM than merely 2 GB over there. Now, this kind of a mechanism of using a batch size of 10 is what is going to consume 6.1 GB. So, typically if I have a GPU of about say 8 GB, it works out good. Now, say that I do not have a GPU of 8 GB, I have a GPU just with 4 GB of space available. Now, let us change this batch size and make it to say 5. So, if this one is 5, then the total space taken by the data and model activations is going to be 3 GB of space, and plus this 100 MB of model parameters. So, that is 3.1 GB of space. Now, 3.1 GB of space is something which is still within the 80% rule. So, 80% of 4 GB is about 3.2 GB. So, I am within that rule. So, with a batch size of 5, I can run it down on a very plain simple GPU which has about 4 GB of RAM. So, that is say one of these commercially available models is an NVIDIA GTX 1050 Ti. With 4 GB of RAM, which can work it down on this kind of a simple example with just a batch size of 5. Now, say you move over to a GTX 1080 Ti which has about 11 GB of RAM, you can definitely increase the batch size to about say 12 or 15 and pretty much do it. So, that is how we actually go into practical aspect of calculating out batch sizes on CPUs versus GPUs. Now, the next part which comes down is your hardware acceleration for compute. Now, typically when we are doing it on the CPU side over there, then I have my model and the parameters of the model which reside on the RAM, and I also have my data present on my RAM. Now, what I do is I do a forward and then I get down my activations and the gradients coming out over there, and we had done a plain simple calculation into what is the total number of floating point operations and everything which it requires. Now, if you would look into it, if you are doing a convolution in the straightforward way, then there are more number of multiplications and the strides and everything which comes down. So, the total number of operations is significantly high. On the other side of it, from our very classical image processing knowledge, we already know that convolutions can be represented in the Fourier domain as just dot products. So, what that would mean is that if I have my kernel, I take a Fourier transform of my convolution kernel, and my image, I take a Fourier transform of my image as well. Then this Fourier transform things can just be done as a dot product, and that is much lesser amount of time. A dot product is just point to point, element to element products between these. Now, that will be taking much significantly lesser amount of time as compared to trying to do a direct compute on my with the cardinal form over there. Now, typically what happens when you are not using accelerators, which is you can have things on the CUDA, but say you do not have a special library called as a CUDNN available over there, or say for your Intel processors there is something called as an MKLDNN. So, if you are not using these MKLDNN libraries or CUDNN libraries, then you are still trying to do it with the classical way, except for the fact that since you have a heavy parallelism in the data and you have more number of cores available, so you are going to push it down onto multiple number of parallel cores. On the other side of it, you are going to reform each of these computations. So, each convolution instead of in the spatial domain, this gets replaced as convolutions in Fourier domain. Convolutions in Fourier domain are just you take an Fourier transform of the kernel and Fourier transform of the image and then do a dot product, which is much faster in terms of compute. So, that is what happens. However, because you are making this Fourier transformed over there, so Fourier transform data is going to take more amount of space. So, typically it is about double the space which it consumes over there, and for your activations as well as for your data. So, this is where it goes. So, the downside is you will be requiring more amount of space. The upside over there is definitely that you would require less amount of time in which you can operate it out. So, this is typically what happens when you are trying to do it on a accelerated form over there. Now, this RAM does not necessarily mean that it is only CPU RAM. If you are doing it on the GPU, then this is the GPU RAM where it works out. So, these are just a block level representation of what happens with each of them, and when using CUDA versus not using CUDA and a CUDNN library versus not, then what are the changes which comes down over here. Now, what we would do is we have a very simple benchmark run down on a very simple algorithm on AlexNet, and so all of you are quite well aware of AlexNet. So, what we are going to do is just look into some of these example case studies over here. Okay. Now, you can see a lot of these bar graphs and stuff. So, let me explain it out. Now, if you look at this part, which is from this 0 on to 80, which is the upper part over here. So, what we have done is we have just plotted down what is the amount of time taken per epoch to execute. So, you do a forward and then do a backward over there, and then within one epoch how much of time is it going to take to execute it. Okay. Now, each of these bars over here is for a different kind of a hardware configuration and a software configuration. So, we have 4 of these experiments which are run down on an Intel Xeon E5 2620V4, which is just a 8 core processor, and the machine which we are using that has 2 of these processors. So, in total you basically get down 16 cores available with you. And then what we do is we either use Anaconda Python and PyTorch, or we use Intel Python and PyTorch, or Intel PyTorch with Python, and these are the different combinations which comes down over here. Okay. The next one which we have done is on an experimental system which is called as the Intel Xeon Platinum 8180, which is a newer version of Xeons which have come down, which have more number of cores. So, 8180 typically has 28 cores available to us, and this particular configuration which we were using, that had 2 of these 28 core machines which work on a pure double precision floating point. Okay. Next, we also tried against 3 different GPUs. So, one of them is Quadro P6000, which has 24 GB of onboard RAM. There is a GTX 1080 1080 Ti, which has about roughly 11 GB of onboard RAM, and the NVIDIA Tesla K40, which has about 12 GB of RAM on it. Now, these are from different generations actually. These 2 are pretty much from the same generation, being Pascals. This is from the Kepler. The intermediate Maxwell is what we do not have over here for the comparison as such. Okay. Now, if you look into it on the other x axis over here is what defines the number of threads, which is the total number of parallel processes which you can call down. Now, typically you would see that if we keep on increasing this number of threads, then at a certain point of time the speed actually increases, the total time taken goes down, whereas again it keeps on increasing. Now, this is one of these machines which we were comparing it down, the one on yellow. Now, that is something which is going to take down lesser amount of time as it keeps on going. Now, you would see that this has about 28 cores. So, at 16 cores is where at 16 threads is where it shows you the least, somewhere over here as well. So, 8 and 16 is typically where we were seeing down least, but then we have not yet looked into the total number of DMA channels available. It is not just the function of core which comes down. On the other side of it, you have these massive GPUs as well, which have almost a similar one, whereas saying that the Kepler is the older version, whereas the Quadro P6000 is the newest version over there. So, that is obviously going to take lesser time. And what does not change is across the number of threads, this does not change, because GPUs do not work in any way dependent on the CPU threads over there. They do with their own acceleration on CUDA and CUDN. So, on the other side we have plotted down the speed up factors and going it down. So, this was a typical example to show you that how different aspects do play a significant role, and for each of them, based on how we are doing a software pipelining and in what order it is doing a DMA call and everything, this is where it changes. Now, this was just a comparative study of say on the CPU, how can you use the best resources and bring down the total time consumed to the smallest possible versus you using a GPU, and can at some point of time your CPU, because if you look into this Intel Xeon Platinums, you would see that they are almost comparable to that of a GPU, and this is an interesting factor, because they are the ones which come down close to a GPU, and you might not even consider using a GPU at any point of time. So, that is what I have till at the end of this one. In the next lecture, we will start with certain other practical aspects which are called as domain adaptation. Can I use a trained model, a pre-trained model available for some other purpose to do another job over there, and then we keep on continuing on to more advanced topics. So, still then thanks and stay tuned.